Yeah, ladies and gentlemen, it's a great pleasure for me to welcome you on our tonight's webinar about the dawn of the hydrogen economy, recent developments and activities. It's my great pleasure to introduce first the organizations responsible for this webinar. This is on the Tunisian side, the Green Hydrogen Society, as well as GIZ and the University of Carthago. And on the German side, it's Hamburg University of Technology, as well as the VDI, as the Engineering Association here in Hamburg, and the Energy Research Energieforschungsverbund also here in Hamburg. So with this, thank you very much for being here, and it's now my great pleasure to introduce our speaker and our program for tonight. We have two outstanding, two interesting, and two very, let's say, innovative presentations. On first, we will have from Marcelo Ambrosio from Fraunhofer IPA. This is the Fraunhofer Institute for Applied Polymer Research here in Germany, a presentation about lightweight composite structures for hydrogen storage application, which is, of course, an important topic because we have tackled this topic about hydrogen storage already, and from that point of view, this is quite important. And we have another presentation from Ali Amanu. I hopefully that I pronounce it at least not completely wrong. I will do my very best, from the university in Quebec, and there from the Hydrogen Research Institute about unleashing the power of hydrogen, revolutionizing industrial mobile robotics and interfactory transport based on hydrogen. So therefore, we see two interesting topics out of the area of hydrogen technology application and parts of the hydrogen provision chain. And with this, I'm very happy that both of them are here. And with this, I would like to finalize my introduction. And it's my great pleasure to pass over to Marcelo Ambrosio from Fraunhofer IAP. And Marcelo, we are very much interested for your presentation. So please go ahead. We are listening to your speech. Thank you.
Yes, good evening, everyone. Martin, thank you very much for the introduction. My name is Marcelo Ambrosio. I'm group lead for design and simulation at the Fraunhofer IAP, Institute for Applied Polymer Research. And I'm counting to the research division polymeric materials and composites. So we deal with the focus composite material, fiber reinforced materials. And today, I would like, first of all, to thank to the organizer for the invitation and to make it possible to participate at this very interesting webinar series. So my topic today is lightweight composite structures for hydrogen storage applications. We have seen in the past webinars that we talked a lot about markets and potentials. Today, I really want to go into the application and show some developments about hydrogen storage at our institute. So first of all, a few data about the Fraunhofer IAP. We are around about 250 employees. We are located in the metropole region of Germany's capital, Berlin and Brandenburg. Our headquarters is at Potsdam. We as PICO are working on two sites, especially Cottbus and Wildau. I'm actually located in Wildau, which is not far from Berlin. And here we can see our brand new buildings that we got last year, and we're pretty proud of it. So everyone is invited to visit us. As we're near the Polish border, we're also working a lot with Polish partners. Also here we have a lot of lightweight technologies located in this border region. So there's a lot of cooperation. How are we set up, organized? So the Fraunhofer PICO is directed by Professor Seidlitz, and we divided our team into main divisions, departments. On one hand side, you find the tailored materials. On the other side, design and process technologies. So first of all, for the tailored materials, we have a polymer development. So we cover high performance polymers recycling and repair technology, microelectronics, and also alternative hardening, curing methods. Then we have Dr. Sebastian Stephan. He's responsible for our semi-finished components as fabrics, bio-based materials, modification of materials for fire retardancy. This is one of our main expertise in this field. And then on the other hand side, design and process technologies. We have my group, design and simulation, when it comes to the holistic design, conception of structural components with composites, but not only the parts, but also the manufacturing processes like automated fiber placement, additive manufacturings. And one of these processes I will explain you today in this webinar. Then we have testing, analytics from mechanical, optical, and chemical testing, fire testing, all kind of testing methods that you can imagine regarding composite materials. And at last, we combine all these competences in the CENALab group, where we deal with hybrid materials, optimization strategies, filament winding of pressure vessels, structural health monitoring, and so on. So our unique selling point at this case is we deliver solutions from one single source, beginning from the polymer development over testing, simulation, up to the part and manufacturing process. So lightweight technology as a key for energy transition. As you know, we have big issues in our world. We have the climate change, greenhouse effects, global warming. The requirement is to reduce CO2 emission, energy savings, and mass efficiency. So in this context, when we have a look on the formula for the mechanical energy, we have the mass, the gravity, and the velocity. Well, gravity we cannot change. It's basically a fixed value. Velocity we want to get slower. So the only thing is what we can do is to reduce the mass or to work on the mass. So that's why the approach is customize materials, design, and processes to achieve the goals in order to solve these problems. So lightweight is a cross-sectional discipline of lightweight design in the fields of the attention of society, and we make use of digitalization and artificial AI, simulation of complex systems to develop our systems of lightweight composites, digitalize product development, digital twins during the developments, with the help of decarbonization, national hydrogen strategies, and so on, as well as biologization of technology and circular economies. So as we can see here, we have different exports in the world, mainly when it comes to transportation and machinery. When we talk about, let's say, Western world, especially Germany or US, we have a high amount of transportation and machinery. And just to give you an idea how important it is to be lighter, or lightweight technologies are very important to contribute to the climate change goals. So when we decrease our weight of components or technology up to 10% only, we are already able to save 3,000 million tons per year of carbon dioxide. Just to give you a brief impression how important lightweight technologies are. So in this specific case, polymer-based composites, what are the advantages and challenges? So as some of you know, we have excellent specific mechanical properties. We are a little bit stronger, for example, than steel, but almost 4 times lighter. We have adjustable properties regarding thermal, acoustics, mechanical, high degree of design and layout freedom, which gives us the possibility also to increase the degree of automation. And in this case, I want to explain why the orientation of fibers, let's say glass fiber or carbon fiber, is important. When we apply some force in fiber direction, we get almost 100% of the fiber performance. And what is shown here in this diagram on the right hand side corner, we have a strongly anisotropic behavior of these composite materials. So As we change the orientation of the material by only a few degrees, let's say 5 degrees, we already drop the performance from 140 megapascal or gigapascal to 120. Yeah, when we deflect about 10 degrees, we only reach the half of the performance. That's why the accurate positioning and orientation of the fibers while designing these composite materials is very crucial for the performance. That's why in our aircraft manufacturing technologies, we have automated fiber placement systems, which I will explain you now in the coming slides. And we use them to build up manufacture parts from aircrafts, not only the parts from the aircraft, but also fuel tanks, as you can see here from NASA, a spherical fuel tank to store hydrogen. For the future, we see that the amount of composite material are increasing very drastically in the manufacturing of aircrafts. So we get 30% mass savings through the use of carbon fiber reinforced plastics. And from the 70s to nowadays, with the modern with the new model A350, we have around about 50 up to 50% more carbon fiber or composite material inside the aircrafts. And due to the pandemic, as you know, we had no aircrafts flying in the air. But after the pandemic, now people will travel again, and we need to gain the goals regarding the fuel consumption and so on. So we need over 35 new aircrafts worldwide, and as you can see, to gain these goals, we need a lot of composite material in future. So to come up to the hydrogen storage application, I would like to explain you our developments regarding hydrogen storage or application as an example of our recent developments for decentralized Power-to-X pilot plan using solar and wind energy. In this case, you can see a very simple and basic scheme of Power-to-X plant. On one hand side, we have a small wind turbine. On the other hand side, we have hydrogen storage, and in between, we will have a control system, electrolyzer, and a fuel cell. I don't want to go deep inside into the other components. I would like to focus more on the wind turbine and the hydrogen storage for this session. So first of all, I would like to start with the low wind, lightweight rotor blade for small wind turbines. We developed that in cooperation with the University of Cottbus and a company, EAB Gebäudetechnik, here in Brandenburg. And what it is all about. First of all, what is the potential for smart wind turbines? I suppose every one of you knows the bigger ones, but actually there's also high potential for smaller ones. And the actual problem is that the recent designed small wind turbines are mostly made for shore regions or higher wind speeds. And as you can see here on the maps for France, Germany, and Tunisia, we have high winds, especially in the coast regions or mountain regions, but everything in between, we can see very low winds. So, and what we also have is that this low power revenue of the wind speeds from 3 to 5 meters per second are not economical for someone who wants to install these kind of small wind turbines. And we also have high costs due to the manual manufacturing processes. Basically, these rotor blades are made of hand laminates, and there's a low social acceptance, especially in urbanized zones, big cities. They don't want to have these small wind turbines everywhere. So what is the actual demand? We need wind turbines, small wind turbines for low wind regions with decreased operating wind speeds to place them in our middle region where we have low winds. We have to reduce the cost of manufacturing in weight, and we have a high request regarding the actual problems in the world for decentralized power supply due to increasing energy prices. So how we solve this problem? we developed a glass carbon fiber shell design. We have a rotor blade system which is 1.5 meter long, so the diameter will be 3 meters. The tower of the wind turbine is around about 10 meters high. And you have to know that when we come up to higher winds at a certain point, the machine has to stop. And therefore we will have some adjustment mechanism in the blades, which are very high in maintenance. And with the optimization of different designs and profiles, we reached a rate reduction of 35%. So our blade decreased some weight from 3.7 kilogram to 2.5 kilogram. And in the same time, we increased the effective surface about 50%. At the same time, and due to our optimizations, we were able to reduce the noise. And what is very special at this point, we manufactured these composite blades with a printed tool, which I will explain you now. So what is the performance? We have 2.5 kilowatt at 8 to 10 meters per second, and a minimum wind speed of 3 meters per second. So as you can see, we already match these low regions here for the installation of this rotor blade. And the specific thing or feature is that we integrated a bend drill torsion to avoid all these adjusting mechanism or brake systems which costs additionally. So in this case, we use the design flexibility and the coupling properties of the carbon fiber or the fiber reinforced plastics to arrange an anisotropic fiber layer, which allows us that while we have higher winds, we will bend the tip of this rotor blade, and at the same time, we will gain a twist in the tip. So this allows us to break down a little bit the rotor blade so that we achieve a kind of self-regulation in this wind system, which makes it much more effective. So we were very successful in this case. I don't know if you can see the videos playing, but we can see that we have, due to the mass reduction, a higher adaptation, a quicker adaptation, acceleration to the wind speed, and less noise emission based on numerical profile optimization. Yeah, we have a field test here near Berlin since June 21. Duration of assembly is around 3 hours, and we measured so far a maximum rotation per minute of around about 500 rotations. And we are very proud that from next week we will have some wind tunnel tests at the Technical University of Berlin. It's a Grovika, it's a big wind channel, and we are looking forward to the results. Here just a short explanation how this printing system works. So we have a large-scale additive manufacturing center. We can print, extrusion print up to 1.3 to 2.3 to 1 meter. So it's quite a high volume with a maximum print rate of 40 kilos per hour. And we printed this tool, which you can see here in the middle for the rotor blade in 7 hours. And what is the big advantage of this technology that compared to recent milling technologies or materials like polyurethane as a block material? We have a cost cutting up to almost 80% using extruded shell and hollow geometries, which also allows us to decrease the weight and energy while moving or production of the molds and production of the rotor blades, so that compared to a full polymer material of around about 40 kilos, we decrease the mold mass to up to 15 kilograms. So when it comes now to the pressure vessels, we have different process technologies for the production of hydrogen tanks. On one hand side, the automated fiber placement, which we saw in the beginning for the production of aircraft components. And on the other hand side, we have the filament winding, which is also a technology to produce these type of pressure vessels. And to just give you a short introduction how pressure vessels are built up. Basically, there are different types of type 1 to type 5. The type 1 is, let's say, the most common or easiest pressure vessels. It's a monolithic metal tank. Type 2 is a perimeter reinforced metal tank. Type 3 is a fully reinforced metal tank. So we not only have the fibers on the outer side, but also on the caps here, on the domes. The type 4 pressure vessel is pretty much the same like the type 3. The only difference is that we have a polymer liner inside instead of a metal liner, and type 5 is a linerless tank made fully of fiber reinforced plastics. So as you can see here, we have a high lightweight potential at type 5, and this is what I'm gonna to explain you now based on an example for hydrogen buses. So why fiber reinforced plastics or composites? In this case, we have a hydrogen bus in the region of Cologne with a tank which has an operating pressure of 700 bars and a length of 3 meters with a diameter of around about 0.3 meters. And when we design it, like for example for type 1, it would like have the mass of 1.7 tons. And as we add some carbon fiber to type 2, as I showed you before, we already decrease to 611 kilograms based on the fibers that we will use. And when we do the same technology with, or the same pressure vessel with the type 5, we will reach almost 100 kilograms of weight per vessel. So as you can see here, the fiber reinforced pressure vessel is up to quite 20 times lighter than the full mass and 6.4 times lighter than the type 2. Here's another example how we updated, let's say, a type 1 pressure vessel, monolithic metal vessel to a type 2 circumferential reinforced metal vessel. The operating pressure of the type 1 pressure vessel is around 11 bar, and just by adding a 0.25 millimeter ply thickness, and so fiber reinforced plastics around the pressure vessel, we triple the operating pressure. Yeah, the ply thickness of 0.25 millimeters on 1 meter is maybe not even 1 kilogram of material that we add onto the pressure vessel, but we gain a triple of the operating pressure, and this is quite impressive. This is also, as I said in the beginning, so important to keep the right orientation of the fibers. So during our developments for pressure vessels, we always use a combined process and structure simulation of winding or laying process. So on one hand side, we have the process simulation with different types of simulation softwares like CADwind, ComposiCAD, Winding Expert. On the other hand side, we have the structural simulation, analytical or numerical, with the different network theories, the classic laminate theory, and also Abaqus One composite modeler, which are specific modeler for composite design. And in the end, we have an end-to-end process and structural optimization of the entire part. So what we get from the process simulation is, for example, the winding length, the material consumption, critical wind angles, gaps, failures, the fiber orientation in each point, the process duration, and also the G-code for the machine. And on the structural simulation, we investigate critical stress areas, maximum deflections in certain regions of the pressure vessels. We also do optimization of the inhomogeneous stress distribution in the boss regions, and the failure analysis of the pressure vessel. So this is the technology automated fiber placement. I just want to give you a brief description how the technology works. So we have a consolidating compaction roll here, which is mounted on the laying head. And from one side, we will have the slit tape. So it's a thin tape made of fiber reinforced material. And we have different heat system, a laser or infrared, to modify the properties of this tape, and some process monitoring systems. And this tape will then be placed, as you can see in the pictures above, on a certain mold, on a tool. And with this technology, we are able to lay up some radio also. We are very flexible in the design, and due to a specific construction here, cut on fly, we're able to do some online cutouts without to reduce the waste, because our material is very expensive. So this is how it works in the practical way. I don't know if you can see the videos running. So here's the example of the evolution of the Type 1 to Type 2 vessel, which we developed here or manufactured here at our site in Wildau. Another process is the filament winding. So here we wind the composite pressures with the rowings. They are more flexible carbon fiber rowings compared to the tapes. So we have an impregnation bath, which you can see back here in the center of the machine, and the rowings, impregnated rowings will be placed perfectly on this polymer liner, which you can see right now. And we have the possibility to manufacture maximum length of 3 meters and a maximum diameter of 600 millimeters for this pressure vessel, which is already quite good dimensions for R&D. So here again, a demonstration how this winding process works. So we start at one point, and as you can see here, the rowing is coming from the impregnation bath through different rolls and gets calibrated onto the liner with the winding eye, specific winding eye it's called in this case, this machine part which transports the rowing. And we have the possibility to input different types of materials, up to 4 dry rowings. We have a temperature controlled bath, resin bath, and we also prepared this machine for towel preg, which is kind of a new technology of tapes. So as you can see, liner is one very important component for the manufacturing, and it's not very easy to get these liners. You will also always have some different type of dimensions and so on. So therefore, we had the idea to print our own liner, which was very successful. As you can see here, first of all, we had the cylinder manufacturing, then the pole cap manufacturing, and by thermoplastic welding, we joined these components. After that, we finished our surface by milling, and we got very good results. On the other hand side, we have another route. It's the caprolactam route. Caprolactam is sort of a precursor for polyamide 6, and by activating it with some activators and catalysator, we're able to mold by rotomolding our own PA6 liner with very sustainable and low energy molds and low temperatures, compared to melt extrusion or rotomolding of melted PA6. It's much more energy efficient. Beside the production of pressure vessels and manufacturing, we are dealing also with the integration of structural health monitoring systems. So we use printed sensors and optical fiber in combination as a dual sensor concept to monitor and evaluate some critical deflections or impacts to our pressure vessels. This is a very important issue when you want to use these pressure vessels in future, especially in the private environments. So this is how we manufacture it. We got some printed and stitched sensor, which we compared to some different types of temperature sensors, which we added to the pressure vessels. So within the winding process, and on the other hand side we have this pressurized test bench with water up to 6 bar and a data acquisition system to evaluate and monitor all the deflections or failures in the pressure vessel. We use the system also to integrate other sensor or, for example, heating elements. We have here a specific rapid prototyping machine which combines the different additive manufacturing technologies. We have a 5-axis system, so we are flexible and are able also to print 3-dimensional electrical circuits. In this case here, we have different projects for aerospace where we integrated some heating elements, for example, for the heating of the cabin or even de-icing of the wings. So you can see that we apply some different types of inks. In this case, it's silver ink. And on the next step, we will see the application of carbon ink, which gives us the functionality of heating. So, and we can manufacture this in a few minutes after hardening, curing of the inks. This system is totally ready for application. So our outlook or vision is in future to combine all these technologies that are presented. So on one hand side, printing of core materials, of molds, then applicate some top layers and structural components by automated fiber placement, and in between integrate functionalities by printed electronics, as you can see here in this picture. So this is still a vision of us. We hope to gain this one day in this case for a specific demonstrator. Yeah, so at least in the last slide, I would like to present our Lausitz Science Park, one of the biggest projects right now in our region, with a funding of around about 250 million euros. 10 years, 8 years project up to 2030, where we combine all technologies, lightweight, hydrogen, infrastructural topics, graduate schools in our region, which is where we are very glad and proud of it. We are developing different types of structural lightweight systems for aerospace, for plant construction, and so on. So this is the activities regarding hydrogen are very dense in our region. Just to give a short sum up, the Fraunhofer Project Group CENALab Center for Sustainable Lightweight Technologies combines also all the technology which are presented here. So we concentrate the activities regarding hydrogen in this project group, which goes to 2026 with a financement of 4.5 million euros. Great. So thank you very much. Please don't hesitate to ask questions, and I would like to give over the word to Martin. Thank you.
Yeah, Marcelo, thank you very much for this very interesting presentation and this wrap up about the ongoing activities. So I learned that, let's say you are on the way to provide cheap hydrogen storage systems, which you print out and then you wrap it, and that's it. Yeah. So maybe in a nutshell, maybe technology is a little bit more diverse and a bit more challenging than this one, but nevertheless, I found it very interesting. Thank you very much for that. We come back to the discussions, and let's later stage before we come to the discussion, I would like to introduce again Ali Amamu. I hope that this time it's a little bit better than the last time. I'm still working on these names. So he is let's say he works with the Hydrogen Research Institute, which is attached to the University of Quebec in Canada. And he will give us a wrap up about the ongoing activities in his institute, as well as a little bit also an outlook about hydrogen activities and hydrogen necessities in, I would say, Canada. I don't know if this is completely right, but we will see. So the floor is yours, Ali. Please go ahead, and we are very much listening to your presentation.
Okay. So thank you so much, Martin, for this introduction, and I'm very happy to be here with you today. to introduce for you and to talk about like an interesting topic. It's like hydrogen in industrial mobile robots. So I will start by introducing myself. My name is Ali Amamo, as you introduced me, Marta, and I'm Innovation and Research and Development Project Manager at Hydrogen Research Institute, like from 5 years. So my presentation, it will be like split in two parts. The first part, it will be like I will try to introduce a little bit the Hydrogen Research Institute and our research works and activities. And second part, I will try to go deeply in like the integration of hydrogen system in the industrial mobile robots. So the Hydrogen Research Institute of University of Quebec in Trois-Rivières was established in 1994, and it's one of the Canada's leading institution in the hydrogen research. So it's multidisciplinary. We have a multidisciplinary team of over 100 to 200 people working in different research fields. And we have an international team from 22 nationality, and we are always like hiring PhD students, master students, and postdocs. So if there are any interest in what we are doing, and we will have more details about what we are doing in the following, we can contact me. You will find my contact in the first slide or my second slide. So now we will move to our research activities in the Hydrogen Research Institute. So we have around 3 big research activities. The first one is the smart networks. It's around buildings, energy, the local demand management, the transactional management, the artificial intelligence, and embedded systems. The second research activity is around the hydrogen technology and clean energy. It's more about chemical and material linked to hydrogen technology. So we work more about around the production and use of hydrogen, electrolyzers, fuel cell, material like catalyst, membrane, electrode, bipolar plates, and hydrogen generator. We work also on the photovoltaic solar energy, the wind power, and the smart microwave. The third research axis is the intelligent electric vehicles, and it's my team. So I'm leading this team with Professor Susu Kilwani, and we have 3 axes in our team. The first one is the self-driving car. The second one is the autonomous industrial vehicle, and the last one is the battery and hydrogen vehicle. In the following, I will go deeply in every axis. For the first one, self-driving cars, the objective is to develop a driving assistance systems by considering the vehicle energy efficiency. So here we develop some adaptive braking system, adaptive cruise control system, forward collision warning, alert system for dangerous situation. Here we are used to develop and to integrate the different hardwares like intelligent cameras, infrared camera, lidar, and radars. We work a lot also to fuse these different sensors and to adapt this kind of technology to the weather of Canada. So, but it's winter, Canadian winter is a little bit complicated, difficult for this kind of technology. And the main focus, also one of the main focus of this kind of for its axis is how to adapt, how to use intelligence to improve the energy efficiency of hydrogen vehicles. So I will give some example. For example, with intelligence, we are able to detect, for example, any stop possibilities. And by detecting stop possibilities, by, for example, detecting the pedestrian in winter conditions or any vehicles or any dynamic obstacles, we are able, based on the driver behavior, to optimize the regenerative braking energy. So with that, we are able to increase the energy efficiency of this kind of vehicles during braking. The second axis is autonomous industrial vehicle. Here also we develop autonomous industrial vehicles by considering the system energy efficiency. So it's as for self-driving car for outside application. Here also we integrate different kind of sensors like lidar, sonar, radar cameras, and we develop localization algorithms trajectory planning models, fleet management models, planner optimization, considering energy efficiency. We develop real-time map update and dynamic route planning, dynamic obstacle avoidance. So it's the first part. It's we develop all the intelligence and the autonomous navigation stack for this kind of technology. And the second part, also we work on the energy and on the propulsion parts. So we develop a smart battery management system for battery-based vehicles and hybrid electric vehicles based on fuel cells and battery. We develop also online energy management strategies and cost strategies. Here also the focus is how to, of course, to match the energy efficiency with the operational efficiency of autonomous mobile robots for industrial applications. The last axis is like the battery and hydrogen vehicle. Here we work on the modeling dynamic behavior, especially in winter, the optimization and characterization of energy sources like the battery, the fuel cell, and the hydrogen generator, the design and optimization of hybrid energy system, design and optimization of range extended for electric vehicles. We have also very good expertise around like the sizing and the online management strategies for different kinds of vehicles, the cold start and the thermal management strategies, and the multi-fuel cell management strategies. Here, for example, when I have my PhD, I get my PhD in 2018 around like the cold start and the energy management strategy of hybrid and hydrogen electric vehicles. And on that time, so we haven't like any partner, any industrial partner interested by like hydrogen and to integrate hydrogen and that on their vehicles. And from 3 years, we see like a big trend of like a lot of interest on hydrogen and to integrate hydrogen in different kinds of vehicles. And we see a lot of big player and big, very important industrial in their fields to integrate hydrogen in their like vehicles. And for example, now we have like different industrial projects asking for the same thing, like for the engineering part, for the sizing, the energy management strategy, and to help them to integrate like hydrogen technology in their vehicles. So we have one project about like integrating hydrogen for airships, for helicopters, for agriculture, like tractors, for buses, and of course also for industrial mobile robots. Here, I will show just a video that give you more details about like our different axes, like with some pictures and videos. So here it's like around hydrogen. We have here, for example, the Toyota Mirai. It's a hydrogen vehicle. We have in Quebec around 50 cars now under one project. Is to check like and to evaluate the effect of winter in that kind of vehicles. And you have also the first here filling and production stations in Quebec. And also we are evaluating like the effect of weather of low temperature on that technology. Here, for example, we have like a climatic room. When we can go under to -50. We will evaluate like also the effect of low temperature and the humidity on that kind of technology. We work here also in multi-stack management to improve like the energy efficiency of the whole system. Here it's like it's Soukelwani, like the leader of our lab is Professor Soukelwani, and it's like here it's like around the industrial mobile robots. So as I explained in the previous slides, we developed all the autonomous navigation stacks in this kind of vehicles in simulation, and we integrate in the beginning in our like experiment vehicle. In the lab, after that, we go to implement all our, after we validate everything on the lab, we integrate on the rail application with this partner. Here, it's the same mobile robots, but working with hydrogen. It's like here, the black and white box is like a hydrogen, but it extends the autonomy of the vehicles. In the beginning, it was like a battery-based vehicles, but it had around 8 hours of navigation, and we extended to 24 hours by integrating hydrogen. Here is for the self-driving car. So we have our own car, but we transform it to autonomous car. So the project is still in progress. We integrate all the sensors and we validate everything, estimation, and we start integrating everything on like the rail vehicle. And as I explained, our main concern here is how to use intelligence to improve the energy efficiency of hydrogen vehicles. So we work on battery-based vehicles and on hydrogen vehicles. And we have like very good projects around this topic also. Okay. So now we'll move to the second part of the presentation. We'll talk more about like the hydrogen in mobile industrial robots. So. And I will start by putting you in the context. So Industry 4.0, also known as the fourth industrial revolution, refers to the integration of advanced technologies such as artificial intelligence, Internet of Things, robotics, and cloud computing into industrial processes. It involves digitalization and automation of manufacturing, and other industrial processes to improve efficiency, productivity, and flexibility. Industrial mobile robots is an important component of Industry 4.0. So that mobile robots are autonomous machines that are able of moving around the factory floor or warehouse to perform tasks such as material handling, assembly, and inspection. These robots are equipped with sensors, cameras, and other advanced technology that allow them to navigate and interact with their environment. The use of industrial mobile robotics can revolutionize like the industrial process by increasing efficiency, improving quality, and reducing costs. They can work around the clock without rest or breaks and can perform repetitive tasks with high precision and accuracy. Can also operate in hazardous environments, reducing the risk of injury to human workers. There are like three kinds of autonomous mobile robots in industry. Like the first one is autonomous inventory robots. The second one is goes to person picking robots and self-driving forklifts. Some of the main topics of the industrial mobile robots include navigation. So the mobile robots must be able to navigate around the factory floor or warehouse, avoiding obstacles and navigating through narrow space. Localization, robots must be able to determine their location in the factory or warehouse to perform tasks accurately. Manipulation, mobile robots must be able to manipulate objects such as parts and tools using grippers and other mechanisms. The human-robot interaction, as robots became more integrated into industrial process, it's important to consider how they will interact with the human workers. The propulsion system that generate power and deliver it to the raw surface, including the power surface engine, as power surface like the fuel cell and the battery, and of course the engine. And the fleet management is the system controlling the autonomous mobile robot fleet operation. That the autonomous mobile robots can be powered with different like sources. It can be like engine powered AMR, fuel cell powered autonomous mobile robots, solar powered autonomous mobile robots, wireless charging, or battery and supercapacitor powered autonomous mobile robots. The more interesting, like between all that source, is like the fuel cell and the battery. And the choice between the battery and the hydrogen depends on the specific application and requirements of the robots or the forklifts. For goods to person picking robots, battery are typically a better choice due to their energy efficiency and small size. For self-driving forklifts, hydrogen is often a better choice due to their longer operating time and ability to handle larger loads that require high power and large energy requirements. Hydrogen fuel cell forklifts are becoming increasingly popular in industrial applications such as alternatives to traditional batteries and gasoline-powered forklifts. This make them a zero-emission alternative to traditional forklifts that emit pollution and greenhouse gas. One advantage of hydrogen fuel cell forklifts is their fast refueling time. In like battery-powered forklifts, which can take hours to recharge, like 1 to 2 hours, hydrogen fuel cell cell forklifts can be refueled in just a few minutes, which reduce downtime and increase productivity. Another advantage of hydrogen fuel cell forklifts is their long operating range. They can operate for up to 8 hours on one single tank of hydrogen, which is longer than the operating time of the most battery-powered forklifts. Battery-powered autonomous mobile robots generally lose a quarter of their charge when the temperature drops from 25 degrees Celsius to -15. Hydrogen-powered forklifts retain their charge and maintain their performance despite low temperature. And in terms of cost, hydrogen fuel cell forklifts are generally more expensive to purchase upfront than battery or gasoline-powered forklifts. However, over the long term, they can be more cost-effective due to their lower maintenance requirements and longer lifetime. So, fuel cell, as we show, it's very good like option for as a power source for the forklifts, and fuel cell are able to generate electrical power with high efficiency, low operating noise, and no emissions. Among like the different kind of the fuel cell, the proton exchange membrane fuel cell is the best one adapted to this kind of technology, because the PMFC has some defined advantages in its favor for electric vehicles. First, low temperature operation and hence its fast startup are desired for an electrical like vehicle or hybrid vehicle. Second, the power density is the highest among all the available type of the fuel cell. The higher the power density, the smaller the size of the fuel cell that need to be installed to the desired power demand. Third, its solid electrolyte does not change, move, or vaporize from the cell. Finally, since the only liquid is in the cell is water, the possibility of any corrosion is essentially limited. However, it also has some disadvantages such as like expensive noble metal needed, expensive membrane, and easily poisoned catalyst and membrane. So the fuel cell has like a lot of advantages, but also presents some disadvantages like the cold start challenges in cold weather countries, the voltage change with the load variation, and the incapability of absorption any energy because it's unidirectional power source. Another main weakness of the fuel cell system is the slow dynamic dominated by the temperature and the fuel cell delivery system, like the pumps, the compressor, the valves, and the hydrogen reformers. So the fast load demand will cause a high voltage drop in the short time, which is recognized as the starvation phenomena as shown in that figure. So for high demand of current or power, you can see like that phenomena, but it's not like it degrades the fuel cell, and it can support also the high demand, requested demand for a high power system. So to fix this problem, the hybridization is mandatory. So it's very important to add another source with the fuel cell as the battery and the supercapacitor, because the supercapacitor and the battery present like a better power density compared to the fuel cell, and the fuel cell present a better energy density compared to other sources. So combining both or three of them together, it can satisfy the fast dynamic load, reduce degradation rate by absorbing peaks, increase the fuel cell economy without sacrificing the performance, improve the powertrain components efficiency. It supports like the power, the load during the cold start, and it gives the opportunity for energy recovery, especially for generate like the braking energy. Another aspect that is very important for high power application is possible. It's like the possibility to have just to be considered under one fuel cell with its auxiliary parts to satisfy the application requirements, or to use like multi-stack fuel cell system integrating two or more low power stacks including auxiliary parts. Like this, considering like multi-stack, it can like match like the survivability and durability and give a higher degree of freedom and flexibility architecture, and also overall operating cost decline and an efficiency improvements. And as you see here, like a high power fuel cell system is not just based on just one fuel cell. It's the fuel cell with the air supply system, the cooling system, the humidifier, the electrical interface, the hydrogen also supply. So it's like a very complex system, and sizing every component here with the fuel cell, with the battery, is like big challenge, but need very optimized algorithms and very good choice for the different like components to cover with the best efficiency, like the requirements, energy requirements of the system. And also by considering like the hybridization and the multi-stack, for example, it's very important to choose also the best architecture here. So there are different architecture like the series architecture, the cascaded, the parallel, or the series parallel. For every architecture here, like they present like some advantages and disadvantages, and the choice of like the architecture is to be based, of course, of the requirements of the vehicle, of the energy vehicle requirements. Another aspect that is very important for autonomous mobile robotics in industrial context is like it presents like the industrial context presents like a repetitive mission, dynamic obstacles, small corridors. So, and the performance of the fuel cell system is highly susceptible to these operation conditions because it will present a frequent start and stop. and that frequent start and stop for that kind of application increase the fuel cell degradation and hydrogen consumption. And as you can see in that figure, the cell stop can present around 33% of the degradation of the fuel cell. So the question is how we can minimize the degradation and the hydrogen consumption from the system point of view by considering just the energy management strategy. And here, so what I present now, so there are like the hybridization, there are also the choice if it's like one fuel cell or multi-fuel cell for high power applications. Also, considering the degradation of the different source by considering like the operational context of like industrial vehicles. So we have the best choice in terms of like all these elements. The sizing and energy management strategy need to be coupled together, and it presents a coupled problem. From a system level perspective, this coupled optimization problem can be classified into 4 categories of sequential, iterative, simultaneous, and B-level. The first one, the sequential, is like the component sizing and power management strategy is optimized in a sequential manner. Usually, the plant or component size should be optimized first before controller optimization. The second one, the iterative, the component size and controller is optimized in an iterative manner. More specifically, given the initial component size and controller parameters, iterative optimization strategy try to improve the initial choice by first improving the component choice without compromising control performance, and then optimize the controller design without compromising system performance until the component size converge. The B level is like it presents 2 nested optimization loops are employed in a B level components optimization strategy, where the outer loop optimizes the plant by changing the component size, and the inner loop is to design the optimal control for each plant selected by the other loop. And the last one, the simultaneous, is like simultaneous optimization involves finding the optimal component size and control in the single loop. Like the B-level optimization strategy presents like the best choice in general because it gives us like the global like solution, and it's compatible with the energy management strategy, real-time energy management strategy, but it presents like it's not simple to implement and with a very high like computation cost and big complexity. But the most important thing, but it will give us the best like the global solution and is compatible for online energy management strategy. So this like part is very, very important for any engineering study to integrate any hydrogen system based on like the application. For example, if it's airships, the most important thing for airships is like to have like a system with the lowest weight. For other application, for example, it's like for buses, the most important thing is to consider the best like sizing and energy management strategy that present the lowest hydrogen consumption with also the best energy in terms of what respect the degradation of the fuel cells to increase like by considering the cost of degradation and the cost of hydrogen. You need to find the best compromise between both. So based on the application and on the construct of that application, we try to consider it on the optimization like algorithms in the sizing and the energy management strategy. And considering like energy management strategy, so there are like 3 big categories, like the rule-based strategies, the optimized-based strategies, and the data strategies. For everyone, there are like some advantages and disadvantages, but the more interesting one is the optimization-based strategies and data-based strategies. So we are used to work and to present different like algorithms based on dynamic programming, in like genetic algorithms, in model predictive controls, and to combine them with neural network and reinforcement learning to propose some online energy management strategies. So I have a lot of articles in that field applied to different kinds of vehicles. Another aspect for mobile industrial robots is like how we can optimize simultaneously the energy efficiency and the operational efficiency of the AMR fleet. Because what I present in the previous slides is how to optimize and to increase the energy management strategy, the energy efficiency of the hybrid system just by an individual focus on one vehicle. Here, Also, in industry like warehouse, you will have a lot of vehicles. So we work a lot in the multi-layer framework with statics and dynamic semantic definition. And the idea is how to improve like the routing of every vehicle to increase the energy efficiency of the global fleet. So we consider a lot of decentralized like architecture. So all the robots communicate together and in real time, like Google Maps. So we try to update in real time like our map with the conflict zone or with a lot of the zone with a lot of traffic to give like the opportunity to our robots to choose the best like routing in terms of energy efficiency. So here on the left, so it's like our mobile robots, like but it's autonomous and intelligent, and also it's like powered with hydrogen, as I explained in the previous slide. So it was like based battery robots. It was like around 8 hours of operation, and with hydrogen, we reached like 24 hours, like without any filming.
Ali, excuse me, can you go a little bit closer to the micro? The voice is very much, let's say, hard to understand. Yeah.
So as I explained, so now, but we are more interested to include that hydrogen tank in our forklifts. So for our forklifts now, it's autonomous. So we integrate all the autonomous like stack, navigation stack on that forklifts, and soon we'll try to also to include our hydrogen tank to be like powered with hydrogen to expand its operational efficiency. Here is my reference, and thank you so much for your attention.
Yeah, Ali, thank you very much for this very interesting presentation about the ongoing activities. And sorry that I interrupt you, but let's say the voice has partly disappeared. So then it's difficult to listen to you, you know, so therefore please apologize. But as I said, it was a little bit hard to understand. Yeah, thank you very much to both of you for this very interesting presentations. And we have learned quite a lot about, let's say, ongoing research and the development. And in parallel, I think we're seeing at the moment that the market should, how should I say, should a little bit uptake these developments. And therefore, let's say on the one hand side, I would like to see a little bit your view, maybe from the German point of view and from the Canadian point of view, how you see the competition between hydrogen vehicles and electric driven vehicles. Because I understood that you do a lot of work in this area, but at the end of the day, if you look at it on an energy efficiency point of view, let's say the electric driven vehicles are much more efficient. And at least with my point of view and with my viewpoint and with my classes, I do see that, let's say, at least in the area where we do some research, we think that, let's say, at the moment, electric driven vehicles are a little bit ahead of the hydrogen vehicles. And if we build up an infrastructure for electric driven vehicles, we would most likely not build up in parallel another infrastructure for hydrogen-driven vehicles, at least not from, let's say, in the metropolitan regions and in the more dense populated or in the more populated areas. So therefore, how is the view from, let's say, this, let's say, competition area for, let's say, the next 10 years? Maybe we start with the Canadian point of view and then we move over to the, let's say, German point of view or European point of view.
So thanks so much, Marta. So I will start by combining like the two sources, fuel cell and batteries. So I say for batteries, it's always like the better in terms of energy efficiency, but for fuel cell, it's better in terms of operational efficiency. Okay, because it could give you like more autonomy and in terms of like autonomy. So also in terms of effect of extreme temperature, low temperature, because we are in Canada, so we have very, very low temperature. Also, the fuel cell is better, is more adapted to this kind of weather because it's less like effective to low temperature. The batteries, also it's possible, but to work with batteries, but it's very affected and it can last around like the quarts of its energy. Also, in term of cost, battery is better than fuel cells, and in terms of degradation, fuel cell present a better lifetime compared to battery. So every one of the two cells present like some advantages and some disadvantages. And to conclude, we say always that for light vehicles, for low power application, battery is the best choice. So you haven't to go to fuel cells because batteries can do a very good job for low power application. But for high power applications, of course, we haven't any choice to go to fuel cells because it will give you like a very good range. And I will give one example, for example, I will give without giving like the name of the partner because it's confidential. But for buses, for example, if you want to make a battery buses, you cannot go more than 400 kilometers. And if you want with fuel cells, we can reach like, for example, 1,000 to 500, 1,500 range kilometers. So in terms of range, in terms of operational efficiency, fuel cell is better for high power applications, and the batteries are better for low power application. So it's like this.
Okay, thank you very much. Marcelo, how you see it from your point of view?
Yes, basically, I totally agree to the opinion of Ali. So for example, I'm driving electric vehicle, and this winter was the first time where I really experienced the decrease of capacity due to the low temperatures. So indeed, we have a problem here, which would not be that problem with the fuel cells. And me as a lightweight expert, I clearly see it that way, that the mass of battery doesn't change over the use. We still transport the same mass back and forth while driving electric vehicles. While using fuel cells or hydrogen, we have much less mass to transport within these systems. So especially if you have a long range applications or high power applications, hydrogen is absolutely necessary in this case for the future. And if you have like low range vehicles for example, in urban cities or urban areas, we also have a quite interesting development from Tunisia with the Baku motors, where we have these small vehicles with a solar energy panel in the top and a battery. So here, it's definitely we have to make the difference between the application, which technology fits better.
Well, thank you very much for that. Well, I mean, you argue, both of you argue very much on the, let's say, vehicle side. I mean, we do some research here at our institute more on the system side, and I mean, then I do see a little bit challenges to provide the necessary, let's say, hydrogen infrastructure to, let's say, feed all these vehicles. When you say, okay, on one hand side, we would like to have the electric driven cars, that means we need an infrastructure for, let's say, powering these vehicles. On the other hand side, we then need an infrastructure for hydrogen, also to feed or to provide hydrogen for this vehicle. So we have to build up two infrastructures in parallel, which is, let's say, quite challenging because both of them are basically new, yeah, or additional to what we have today. And therefore, I have a little bit, let's say, at least concerns, not my doubts maybe, but at least concerns that this will happen on a very short notice, because to build up infrastructure is always a long-term business. Yeah? So therefore, I fully agree what you said. I just would like to put a question mark, not on the vehicle side, but more on the infrastructure side, how this fits together and how this works out. So maybe you can make a comment about that, if you agree or not agree. I mean, and then let's say, yeah, maybe we start with this time with Germany, if this is fine with you, Ali, and then we could move over to Canada.
Yes, so this what you said is it's totally right, that it's very critical and demanding to launch these two infrastructural networks, but on the other hand side, I see it also as a chance, because I think in future we will profit from both sources, let's say. and we will also have the chance to rely on different technologies in case, because I'm pretty sure that even if we decide only to go for electric vehicles, even that would be too critical to put all this energy in one system. When I speak for Germany, especially now, when everyone wants to load the cars, the entire system would break down. So that's why I think it's a good alternative to use also other energy sources like hydrogen to get a sort of equilibrium in this energy transition.
Okay, thank you very much, Marcelo. Ali?
Okay. So it's the infrastructure is very important topic, because without infrastructure we cannot have hydrogen vehicles in the roads. But the response, I think, is also linked to the first question, to the application. We want to have the infrastructure, for example, for light vehicles or for high power and long range vehicles. So if you want to have it, for example, for light vehicles, it will be a big challenge, because you need to put a lot of filling station and production station everywhere in the city, and it's really a big challenge. For example, here in Canada, from 4 years, I'm managing one project. It's like the governments buy 50 cars and put the first filling station and production station in Quebec. It's like around 150 kilometers from Trois-Rivières, from where we are. And it was a big problem to fill the vehicle every time. So if you go to there and you come back, so we lost around the half of the autonomy. And so it was a big challenge. It wasn't possible. And the governments put a lot of money to increase the number of that kind of infrastructure, 2 or 3 others, because it's very, very expensive, the production filling stations. And they say that they put a plan that they will have some big production stations, and after that they will decentralize a lot of filling stations somewhere in different cities. But it will be also still complex and not very logical to have enough filling stations to feed all the hydrogen vehicles. So with time, I see that the governments and people start to understand that it's better to keep light vehicles for batteries, because the autonomy was around 300, 400. But now see, we have some light vehicles, but with autonomy of 600 and 700 kilometers. So it's very good, and it's very interesting for this kind of vehicles. So it's better to focus on the high power and the long range vehicles, as the airships, the boats, the train, and for example, forklifts, as I explained now. And for that, it's easier to put some decentralized filling or stations, because it will be just near to that application, instead of having it everywhere in the city. It's I hope that it's clear. So it's better to focus on the high level, the high power and the long range application. It will be easier in terms of infrastructure.
Okay, thank you very much for this view. I think let's say the European or the German view and the Canadian view is not so much different. Yeah, it looks like, yeah. So at the end of the day, it's also an international development, and I think we can learn from each other, because the challenges what are ahead of us to face climate change is, let's say, that we cannot, do all the competition. So we have to work together to find smart solutions. Well, what I would like to come slowly to an end, but before I finalize the meeting for tonight, I just would like to understand from both of you where you see in the, let's say, mobility sector, based on hydrogen, the most important challenges in the next 10 years. What is needed and what is necessary to be solved? What is necessary to be realized? That, let's say, we do see a certain share of hydrogen, let's say, in the long distance heavy duty vehicles, for example. If we assume that this is the market which, let's say, will be quite important to, let's say, be defossilized in the next 10 years. So where do you see the most important, let's say, research challenges on one hand side, and the most important challenges on the market side that this will happen? Can we start with Germany, Marcelo, or should we start with our colleague from Canada?
Well, I don't mind, Ali, if you want to start, give you the word. But in my case, as I can see, I also see that hydrogen application, especially for trucks or heavy duty vehicle, is definitely a future option. For my side, I can speak for the development of the hydrogen pressure vessel. So there's a big issue regarding the security of this pressure vessels. For sure, we already have very good developments. The pressure vessels are pretty safe. But when we increase the production lines and the number of produced pressure vessels, it's very important to include sensor systems, structural health monitoring to make to make it safer, the operation of pressure vessels. And I also think that in the end, it's the easiest thing is like to implement this technology into the vehicles. But as we said in the beginning, I see much more problems or questions in this infrastructure and delivery of and production of hydrogen and these quantities to reach or to meet the demand of the markets.
Okay, thank you very much. So Ali.
So I agree with Marcel about like the infrastructure is the big challenge now, about the production and the filling infrastructure. So it's the first like point, but we need a lot of work, and it needs a collaboration between like the governments, like the institutions, the industrial, all of them need to work together to increase like the infrastructure. And the second part is like the cost. The cost is still like very high, and also I hope and I think also with time, with like with this interest of all the people about hydrogen, with time for sure the cost will reduce, and also they need like some research, more research about like material, about and the fuel cells and electrolyzers to increase also to reduce a little bit also the cost of these components.
Okay, thank you very much for that. So then I think we can slowly terminate or finalize our session for tonight. Maybe the very last round. When you think 10 years ahead from today, so let's assume we are in 2023, 2033, something like this, 2033. What do you would expect related to the share of hydrogen vehicles, related to the overall, let's say, ground-based transportation sector? I think it's 5%, it's 50%. What do you see it? What you would expect in, let's say, 10 years' time? Maybe we start this time with Canada, huh?
It's a little bit hard. It's a little bit hard to respond to this question. But what I see, for example, in Canada, they put like one like objective on 2023 to transform as much as possible of gasoline like vehicles to electric vehicles. And as I said, for light vehicles it will be batteries, but for heavy vehicles it will be hydrogen. So for sure hydrogen will take a big place from now to 2023, but how much? It's a little bit difficult to respond to that question.
Marcelo, how is it from?
Yeah, I also agree. It's especially regarding the actual situation in Europe and the world. We get perturbated by a lot of crises, and we cannot see in the future, also in the near future, how this is going to end up. But optimistically, I think that we will reach in 10 years around about an increase of 15 to 20% of hydrogen usage in a common way, let's say, in our infrastructures, in our society. I hope at least that we gain this goal, because 20% is already a lot, and I hope that we will reach that.
Okay, then let's assume that we achieve these goals, at least for the fact that, let's say, we have to face climate change. And if I understood it right, there is on a yearly basis, there is the climate press conference from the German weather service. And they announced now a figure that in Germany we see already an increase in temperature from 1.7 degrees C relative to the pre-industrial times. And if this accelerates like it has been accelerated the last couple of years, you know, then I mean, then we are in 2035 already with 2-degree increase. And so when you look around, especially in Brandenburg, they have a lot of problems with drought and a lot of problems with missing rain. And then I think we get more and more problems. So from that point of view, we have to, let's say, join our forces to, let's say, transfer our energy systems to a more sustainable one, to a more climate sound one, and to a more, let's say, to a system which is, let's say, also able that our childs and the childs of our childs are able to deal with it in a peaceful way. Anyway, thank you very much to both of you, to Marcelo Ambrosio and to Ali Mamu. Sorry, I still have to work on this. Please pardon me here. Sorry for that, but with names, you know, in my age, it's getting more and more difficult, you know. So thank you very much to both of you for this very nice and very interesting presentations about the ongoing research activities. I mean, what you do in your labs, this will be most likely pop up in industry a couple of years later, and then it will pop up in, let's say, in our daily life also a couple of years later. So from that point of view, we have a nice insight into what is coming up or what might come up in the years to come. With this, thank you very much again for both of you. And before I terminate and we switch off the YouTube channel, ladies and gentlemen, mesdames et messieurs, señores y señoritas, please be aware we have 2 more webinars of this series in this winter term to go. And this is next week. We will have country reports from the MENA region. So I'm very happy to announce that we have a country report from Jordan and a country report from, let's say, from Algeria about the ongoing activities in, let's say, hydrogen. And then the week after, which is then the last one, the last webinar in this winter term, we have a country report from Egypt, from Chile, because they do quite a lot in this area, especially with Porsche, as you might know. And then, let's say, a country report from South Africa. Also, there are some activities ongoing. And last but not least, about the International PDX Hub, which is, let's say, powered by GIZ. With this, I would very much appreciate if I can welcome you again next week, same place, same time. And with this, thanks very much again to Ali and Marcelo. This is more easy to pronounce. So yeah, to my regards to Brandenburg and to Quebec. And with this, thank you very much again to the organizer, especially to Wolfram Tuschewitsky, and of course to Shukri Aslush for helping us to get this happening. And with this, I wish you everybody a beautiful evening. Enjoy yourself and